Hi everyone, my name is Liam Kirkpatrick. I'm a graduate student at the University of Washington. Today I'm excited to chat to you about my current project, which is looking at three-dimensional layering with electrical conductivity measurements, or ECM, in the hunt for oldest ice. This project is funded by the Center for Oldest Ice Exploration, or COLDEX, which is a science and technology center funded by the National Science Foundation. I'm also really reliant to the National Ice Core facility funded by the National Science Foundation. So this project is taking place at this spot in Antarctica called the Allen Hills. I've showed kind of roughly where it is with this red box on the map of Antarctica. And then I've zoomed in and showed the location of two cores, Allen Hills Ice Core, ALHIC 2302 and 2201. So these are two cores that I've looked at, and I'll show some data from in this plot. As you can see, this is a really bizarre spot where you can see that blue tinge in the satellite imagery there. And that's because this is a spot that's so windy that we're actually kind of wearing away the snow and getting down to the bare blue ice that's coming up from deep inside the glacier. So we're finding really, really old ice at the Allen Hills. Here I just picked out two news headlines that showed this. We're up to about 6 million years old. Which is way, way older than the oldest ice core before this project, which was only 800,000 years old. However, unlike a normal ice core, we're also learning that this old ice has been folded in this spot. So we're not going somewhere where we drill down and it just gets deeper it gets older the deeper we go. Instead, we're somewhere where the layering has been folded up. And here I asked ChatGPT to illustrate that with a breakfast pastry for us. So you can imagine this adds some complications. We need to figure out the ordering of the ages and how the layer structures interact with the proxies like CO2 or temperature that we're trying to measure. And so if you imagine we drill our ice core through this cinnamon roll or through the glacier, and that's really all we can see. So we can only see that layering. But we can learn a lot about the overall folding just from this little snapshot. And so that's what we're going to be trying to do today. So to do this, we're applying electrical conductivity measurements in 3 dimensions to understand layering and folding. What does this look like? Well, I've got a little video going on the right of this machine just scanning back and forth, and sometimes I have to reach in with my hand and jiggle the electrodes to make sure they press in on the ice. But basically what we're doing is taking a pair of electrodes and we're pressing them onto the surface of an ice core, and we apply a constant voltage and we look how much current flows between them. Which changes based on the acidity and the ion content of the ice. And so on the left here, you can see we've got an ice core that we've cut into quarters, and here we've got 2 of those quarters, and we're going to scan perpendicular faces on those quarters to build ourselves a 3-dimensional map of the conductivity, and so of the layering in the ice. What does that look like? Well, here's some of the first images I made. Applying this technique. And so we can see really clear layering here. This layer in blue, which is a layer of higher conductivity, really pops out. And then we've got this layer in red, which is much lower conductivity. You'll note this layer isn't flat though, it's dipping. This layer actually dips at about 45 degrees. And so this has some really big implications for us. One is that we can use this to study how layering changes over a long section of the core. So this is kind of what I talked about earlier, going all the way through our cinnamon roll. And so we can watch here, we've got our quarter core, and we've done multiple segments back to back. So the white gaps are the chunks between the segments that I can't measure. And we're going from 24 meters deep in an ice core and scrolling down. So right now we're at 29 meters, 30 meters. And so you'll see in some of these, the layering isn't really clear, but in other sections, the layering really pops out, like this one here. You'll also see the layering isn't flat. It's actually really steeply dipping. Here it's about 70 degrees. So that's, if 0 is flat, 70 degrees is pretty steep. But we see that it's consistent over this entire stretch of ice, which really helps inform how we sample the ice and how we interpret the climate records that we're building. I really like this section as well. Really clear, strong layering that really pops out at you. All right, we'll keep on going. We can also use this 3D electrical conductivity measurements to zoom in on really fine scale layering. So this is a figure I showed a little earlier. And the question I want us to think about here is, let's say you're a scientist and you're trying to figure out the relationship between CO2 and Earth's temperature. And so you might cut one chunk of ice and measure a temperature proxy to reconstruct Earth's temperature, and another chunk to measure the CO2 content. But you want to make sure they come from the same layer, so they come from the same time period. And you can see that's not really easy to do, because this layering is invisible to the naked eye. And so we've been working on methods that we can use these electrical conductivity measurements to inform how we cut our samples, so we can coordinate and build this kind of comprehensive picture of what was going on in Earth's climate. So here we've got a slightly complicated figure, so we'll walk through it. On the y-axis, so the up and down, we've got the depth in the ice core. And so we're at 155 meters down to 155.4 meters. So this is only a 40 centimeter chunk of ice. On the left, we've got our electrical conductivity measurements. So we're kind of looking top down at a section, and then across that is just the distance across the ice core. And then the boxes represent 3 different sets of samples in brown, orange, and purple that we cut from this ice. And so with that, we measured the water isotope content, or the delta 18O. And this is a proxy for the temperature when the snow that formed that ice first fell. And so on the right, I've just kind of thrown in a nice help for us. Colder is to the left and warmer is to the right for these 3 different sets of measurements. And so there's a data point on the right plot for every box on the left plot. And you can see when we first look at this, these 3 sets of data look nothing like each other, even though they're the exact same proxy measured on the exact same piece of ice. And that's because the layering isn't flat. But the good news is we can rotate our layering to go from tilted to flat, which will then hopefully line up our samples. And so we can test that like this. So now we're going to rotate our layer until the same layer is at the same depth all the way across the core. And you see as we do that, the water isotope signal on the right-hand side also lines up really well. This also tells us that in the middle of that layer, we have ice that's just a little bit colder, or was a little colder when it formed than the rest of the ice core section. So we hope this new 3D electrical conductivity measurement tool might help us unlock even better records from this really old ice. Thanks for watching.